The Apollo program, initiated by NASA in the early 1960s, aimed to fulfill President John F. Kennedy's ambitious goal of landing a man on the moon before the decade's end. This monumental undertaking was not just about exploration. It was a key element of the United States' efforts to assert its technological prowess during the Cold War. The main linchpin of this dream was the Saturn V rocket, a marvel of engineering that ultimately made lunar landings possible. The Saturn V rocket stands as one of the largest and most powerful rockets ever successfully flown. Towering at 363 feet tall, it was roughly the height of a 36-story building. Its design was based on the principle of multi-stage rocketry, allowing it to shed weight as it ascended through the atmosphere. The first stage, known as the SIC, produced an astonishing 7.5 million pounds of thrust, generated by 5 powerful F1 engines. This immense force propelled the rocket through the dense layers of the Earth's atmosphere. Following the first stage's burn, the second stage, or S2, ignited its 5 J2 engines, which provided thrust to continue the journey into space. Finally, the SIVB stage took over to push the Apollo spacecraft toward lunar orbit. In terms of payload capacity, the Saturn V could carry approximately 310,000 pounds, enabling it to transport astronauts, equipment, and scientific instruments needed for the mission to the moon. This payload capability was essential for the ambitious Apollo missions, which required the transport of not only the lunar module, but also sufficient supplies for astronauts during their time on the lunar surface. The development of the Saturn V was not isolated. It was a concerted effort involving thousands of engineers, scientists, and technicians across the United States. Major contractors, including North American Aviation, IBM, Rocketdyne, and the Marshall Space Flight Center, played crucial roles in the design and manufacturing processes. The cooperation and collaboration among these organizations epitomized the spirit of the Apollo program and showcased what could be achieved when diverse teams focused on a common goal. At the height of the space race between the United States and the Soviet Union, the Saturn V rocket became symbolic of American ingenuity and resolve. The successful launch of Apollo 11 on July 16, 1969, marked a pivotal moment in history, culminating in the landing of astronauts Neil Armstrong and Buzz Aldrin on the moon's surface just 4 days later. As we look forward to future missions, such as Artemis II, understanding the legacy of the Saturn V rocket provides vital context to our ongoing journey of exploration beyond Earth. The development of the Saturn V rocket was a complex and ambitious endeavor that marked a pivotal moment in aerospace engineering. In 1960, NASA established the Marshall Space Flight Center in Huntsville, Alabama, to oversee the development of rockets, including the Saturn V. This new center was tasked with not only meeting the demands of the Apollo program, but also integrating advanced technologies that had never been used in rocketry before. At the forefront of the Saturn V project was Wernher von Braun, a key figure in American rocketry. Originally a German engineer who had worked on the V-2 rocket during World War II, von Braun was instrumental in the transition of rocket technology from military to civilian applications. He and his team at Marshall Space Flight Center brought a wealth of knowledge and innovative thinking that would ultimately shape the design and capabilities of the Saturn V. Alongside von Braun were thousands of dedicated engineers, technicians, and support staff from various contractors, including North American Aviation, IBM, and Rocketdyne, who worked diligently to transform ideas into reality. One of the initial challenges faced during the development of the Saturn V was balancing safety, performance, and cost in design and manufacturing. Given the unprecedented scale and complexity of the rocket, engineers were tasked with ensuring it could withstand the stresses of launch while also achieving the necessary performance for lunar missions. Each stage of the Saturn V underwent rigorous testing to validate design choices and ensure reliability. This included everything from engine tests to structural tests of the rocket design itself. Additionally, the ambitious timeline of the Apollo program added pressure to the development process. The need to rapidly advance research and production presented logistical challenges, as engineers needed to collaborate closely with manufacturers to streamline construction and assembly processes. Effective communication and root cause analysis became vital as teams sought to resolve issues that arose during development. Propulsion was another critical area where challenges emerged. The Saturn V's first stage, powered by 5 F1 engines, generated 7.5 million pounds of thrust, the most powerful rocket engines ever built at the time. Ensuring these engines operated safely and efficiently was paramount, leading to intensive design refinements and rigorous testing protocols. As the Saturn V project progressed, it became clear that it was not simply a rocket, but a manifestation of teamwork and innovation, embodying the spirit of collaboration necessary to achieve space exploration's most significant goals. The lessons learned and the efforts of countless individuals ultimately prepared NASA for its most ambitious undertaking, landing humans on the Moon. The success of the Saturn V rocket can be attributed to the extensive collaboration between NASA and various contractors. Notably, companies like North American Aviation, which later became part of Rockwell International, and IBM played pivotal roles in its development. North American Aviation was responsible for the construction of the command and service modules, essential components that house the astronauts and manage their activities in space. Meanwhile, IBM's instrumentation system, embedded within the Saturn V, was crucial for guidance, navigation, and control during the mission. This symbiotic relationship between NASA and these contractors exemplified the kind of teamwork necessary for undertaking such a monumental task. However, the journey to creating the Saturn V was fraught with challenges. One of the most significant hurdles was maintaining a strict timeline while ensuring the safety and reliability of the rocket. As engineers worked diligently to develop rocket components, they encountered a variety of technical issues. For instance, there were problems related to the F1 engines, the powerful engines that propelled the first stage of the rocket. These engines experienced difficulties with combustion stability and component integrity, leading to delays in testing and production schedules. It quickly became apparent that the complexity of the Saturn V's design presented unanticipated obstacles. Rather than allowing these setbacks to derail their progress, team members implemented a solution-oriented approach, employing active problem-solving teams that focused on identifying and addressing issues as they arose. These teams were composed of engineers and specialists from different departments and contractors, fostering an environment of collaboration and innovation. By encouraging open communication and brainstorming sessions, the teams were able to devise alternative solutions. For example, to resolve the combustion instability in the F1 engines, engineers conducted a series of modifications that improved airflow dynamics and engine performance, ultimately leading to successful test firings. Moreover, scheduling delays were managed through careful planning and prioritization of tasks. NASA held regular progress reviews with contractors to ensure that everyone remained aligned with the timeline and objectives. This collaboration helped to maintain momentum even in the face of adversity, as teams worked together to troubleshoot and adapt to changing circumstances. Throughout this process, the spirit of inquiry and determination among engineers and contractors not only helped the Saturn V project advance, but also laid the groundwork for future missions. The collaborative efforts that address the challenges of the Saturn V are a testament to the ingenuity and teamwork that have characterized human space exploration. As we look forward to the Artemis II mission and beyond, this legacy remains a powerful reminder of what can be achieved when diverse talents unite in pursuit of a common goal. On July 16, 1969, the world witnessed a monumental achievement in human history with the successful launch of Apollo 11 aboard the Saturn V rocket. This mission marked the first time humans would set foot on the lunar surface, an endeavor that had been envisioned for decades. The Saturn V, towering at over 363 feet, was not only a feat of engineering, but also a representation of unparalleled teamwork and determination across multiple organizations and sectors. As the Saturn V lifted off from Kennedy Space Center, it delivered an unprecedented 7.5 million pounds of thrust, showcasing its incredible power. The first stage ignited, propelling the rocket through the dense atmosphere, while the F1 engines performed with remarkable reliability, having been meticulously refined throughout the development process. The successful execution of this launch set the stage for the historic moon landing on July 20th, 1969, when astronaut Neil Armstrong became the first human to step onto the lunar surface. The performance of the Saturn V during this mission established a legacy of reliability that would be crucial for the subsequent Apollo missions. After Apollo 11, the rocket continued to carry astronauts safely beyond Earth's orbit, ultimately enabling missions like Apollo 12 and Apollo 13, each of which benefited from the extensive data collected from previous launches. The Saturn V not only delivered payloads to low Earth orbit, but also played a pivotal role in delivering scientific instruments, lunar modules, and astronauts directly to the moon. The impact of the Saturn V extends beyond individual missions. It transformed engineering practices and advanced technologies. The collaborative nature of its development fostered an environment where innovation could flourish. Engineers, scientists, and technicians from diverse backgrounds contributed their expertise, pushing the boundaries of what was possible in rocketry. This spirit of collaboration has continued to influence the field of aerospace engineering, laying the groundwork for international partnerships in modern space exploration. As we reflect on the Apollo program and the Saturn V rocket, it is clear that these milestones were not just about advancing technology. They also embodied human ingenuity and a collective vision. The lessons learned during this era contributed to future missions, including NASA's Artemis program, which seeks to return humans to the moon and ultimately explore Mars. The Saturn V was more than just a rocket. It was a symbol of what can be achieved when humanity unites in pursuit of knowledge and exploration. The legacy of the Saturn V continues to inspire the next generation of dreamers and explorers as we look to the stars. The construction of the Saturn V rocket was a monumental achievement that evidenced not only technical prowess but also the power of collaboration among thousands of engineers, scientists, and technicians. Every aspect of its design and assembly demanded innovation, as the challenges were immense. One of the most significant hurdles was the need for a rocket capable of carrying humans to the moon and safely returning them to Earth. The Saturn V, standing at 363 feet tall, became the tallest, heaviest, and most powerful rocket ever successfully flown. The project began with the consolidation of various teams under NASA's guidance, including those originally working on earlier rockets, such as the Juno 1 and Redstone. The giant leap to the Saturn V required a rethinking of materials and engineering processes. Lightweight materials became critical. Engineers turned to aluminum alloys and high-strength steel to reduce the rocket's overall weight without compromising structural integrity. Rocketdyne was pivotal in the development of the F1 engines, which provided the first stage of the Saturn V with an incredible 1.5 million pounds of thrust. Each F1 engine was a masterpiece of engineering, featuring innovative cooling methods to prevent overheating as they burned vast amounts of RP1 and liquid oxygen. Coupled with the engine's design was the importance of quality assurance. Every part had to undergo rigorous testing to ensure reliability under the extreme conditions of a launch. Collaboration extended beyond internal teams. NASA partnered with contractors like North American Aviation and Grumman Aircraft Engineering, bringing in expertise from different fields. This partnership led to efficient problem-solving, as engineers shared insights on everything from guidance systems to structural components. This collaborative spirit became essential when unforeseen challenges arose, such as the need for extensive wind tunnel testing to address aerodynamic issues. Safety was at the forefront of every decision. The tragic Apollo 1 accident underscored the need for stringent safety measures. Following the lessons learned, the Saturn V benefited from redesigns and thorough testing protocols, reinforcing the idea that while speed to the moon was critical, safety could not be compromised. As parts of the Saturn V were constructed in various locations across the United States, from the Marshall Space Flight Center in Huntsville, Alabama, to the Kennedy Space Center in Florida, logistics became a challenge itself. The integration of these parts into a coherent whole required synchronizing the efforts of thousands. Eventually, the rocket was assembled in the Vehicle Assembly Building, a facility designed specifically for this purpose. The legacy of the Saturn V is felt today as it laid the groundwork for modern space endeavors. It demonstrated that through teamwork, creativity, and perseverance, humanity could achieve what once seemed impossible. As we push forward with the Artemis missions, the lessons learned from the Saturn V project remain a beacon of hope and a testament to collaborative achievement in space exploration.